Vishal Chatrath, co-founder and CEO, QuantrolOx, onto the stage. With over 27 years of experience in deep technology, Vishal is at forefront of developing automation software to accelerate the scaling of quantum computers. Please join me in welcoming him as he shares his insights on the future of quantum technology.
Firstly, a very good afternoon. The day started with the morning sessions. It was very nice to hear from Dr. Narayan Murthy, Professor Raghavan, and Lakshmi Bharatman, Dr. Sanjay Vandrekar, Dr. Pillai, Dr. Rajan, Ms. Misha Mehdi, and of course, Colonel Nath and Amit Saxena. And I would also like to acknowledge here the amazing amount of energy that Amit has, that he's always organizing, planning new things, so it's very encouraging to come here. So out here, I will talk about the need for qubit automation and how it can be used, and it's almost like a fundamental thing that we need to do to be able to win the race towards building practical quantum computers. And because one benefit you have of being a CEO of a company, that you can escape all the difficult technical questions. So in case there are any more difficult technical questions, I will take them, and we'll be happy to organize an online session with the rest of the team where we can show you the live demo. In the course of what I'm going to be talking about today, I want to briefly talk about the state of the quantum computing industry, and then also talk about building the capabilities, because we are at a stage out here in India, like the rest of the world, where it's important to really build out the capabilities of quantum computing so that in the next 5 years we can really have a strong part to play. I would also like to talk about open architecture quantum computing, why that's important, what are the key challenges to scaling of quantum computers, why, and also show you a video, because I couldn't show a live demo because of the restrictions on the internet, of our product Quantum Edge. And then I would also briefly like to finish that with talking about how open architecture and automation is the bits that we are planning to build India's quantum computing platform. So starting with that, many of you might have seen this kind of particular slide from McKinsey, which says that there is a potential of a value add of anywhere between $1 to $2 trillion by 2035 from quantum computing. These numbers are always debatable, but the main thing out there is there's a commercial side to be there, and we as India need to really go after that. The status today that we have is that we don't have any useful quantum computers, so everybody's trying to basically build them. They're still very early. We still need to do a lot of work on improving the qubit quality and also being able to build systems with large enough number of qubits. Also with respect to HP quantum technologies, while you've heard a lot about it, there are no true scientists who work on it who can seem to agree what it should look like. There are very kind of different ideas how the architecture should be on HPC quantum, a hotly debated topic. Components like QPUs and electronics are evolving so fast that if today somebody was to come to you and try to sell you a full stack quantum computer, you can be guaranteed that in the next 12 to 24 months it will be obsolete. So that's also one of the drivers for open architecture, so that you can replace components as and when the new ones come. So my main message when I start here is that we have everything to play for. Even though you hear news about breakthroughs by IBM, Google every second day, we are still in a place where if we start seriously today, within 5 years we'll be working with the best in the world. Briefly also talking about the status of the quantum computing in India based on, again, my view. From what I observe, if I have got certain things which are incorrect, do excuse me, and if you want to correct me, please do that too, so I can update my presentation. So what I see from my vantage point is a lot of kind of independent quantum computing program projects in the early stages. There is not yet any serious initiative towards productization, and that's important, and I'll talk about that as I go along. There is still a small window of opportunity to start to build and deliver indigenous products and solutions that will make Bharat an integral part of the global supply chain. And that's absolutely important because export controls are happening, and they're happening very fast. Being based in Finland, my company and myself, we are part of consortia of the UK, the European, and also the US quantum consortia. And I can tell you that almost every month, export controls is a strongly discussed topic. The reason why people are trying to sell you quantum computers is because they're not useful. But the day they become useful, people will stop selling you quantum computers. So I think right now it's all about funding somebody else's development by buying their computers. Timing is key. The longer we wait to build these competitive products and start shipping them outside, the task to catch up will become exponentially harder. We do have some competitive components here, like the Rudra server, which we are working with C-DAC to package it in an intuitive way or in a new way so that we can put together some quantum solution and start to sell it internationally. So at least we make a mark as a supplier of quantum computing products globally. Of course, there are companies like, is it called QNew, which is doing QKD, which are already shipping products, so I do want to acknowledge that. In terms of building capabilities, what capabilities do we need to build? We need to have good quality quantum materials. We should be encouraged by the fact that we do have organizations like CMET here in Pune that's working on it. And once we have good quality quantum materials, we need to be very good at the kind of fabrication techniques. Sooner or later, we need to have our own fabs because the core IP, like semiconductors and also in quantum, is not just in the actual design of the QPU, but the actual the recipe that you have to be able to make those chips. That's why TSMC and all these large foundries are incredibly secretive. They will never tell you what's the recipe under which they make these products. Then, of course, there are the quantum control methods, because it's through qubit control we are able to extract the maximum amount of gate fidelity for those quantum operations. Automation is required to speed up the entire process. I'll talk more about it. And eventually we want to get to a place where the operations of quantum computers should be completely autonomous, so we don't have to manually recalibrate them. Control electronics is also a hot topic. C-DAC is already doing work in that, where the heat dissipation is still high. We need to be able to reduce that from power consumption. But also when we talk about the cryo CMOS side, the heat dissipation has to be low enough so it doesn't heat up the actual fridge, which has your superconducting qubits. Similarly, synergy between hardware and software and hybridization of HPC are also important topics. Now, in terms of starting any particular quantum program, you have to start by building some sort of a golden system. And why do I call it golden system? It's a reference system that we know works well. And every time we have a new component, we want to check, is it competitive? You remove one component, try it with X, and one by one you try to bring it up. But at the same time, such a quantum reference facility has to have interchangeability of the components. And like, it shouldn't mean that if you replace one control or electronics with the other, you take months and months to get the system up. It should be a matter of hours. And lastly, it has to be on open architecture principles. And by that I mean there has to be some common, well-defined interfaces. And we can't wait for the standardization bodies. We can't wait for IEEE to come up with a standard in 2045. We have to step forward and make de facto standards. And there also learn from countries like in China, how they did it. I was at Nokia at that time trying to sell the telecom equipment. And what the Chinese did is just came up with their own standards. If you want to sell in China, do that. It wasn't anything that was technically kind of beneficial, but it forced everybody to build some common, basically interfaces, which they then use later to be able to slow everything down and then ship their products to the international market. So there's a reason why Huawei is the #1 telecom supplier. We have to learn how they operate it and use that to build our the quantum computing industry. Then the quantum reference facility has to be able to be really at the heart of doing your quantum materials engineering, quantum computer engineering, and quantum computing science. So effectively, all across the ecosystem, people should be able to use these facilities. We don't need one, we need a lot of these facilities around. So moving to open architecture, like why do we need it and what is it? So I always like to go back to the quote of Professor Feynman, that what I cannot build, I don't understand. So you cannot really understand how quantum computers work unless and until you build those quantum computers. And that's the discussion we've been having for the last few years with C-DAC, that as the first step, we should buy all these individual components, ship them to India, work with C-DAC and the other organizations in India, and build the quantum computers step by step. And then we have some experience as an organization at QuantrolOx. We have our own lab. I'd like to show what we do there and why that's absolutely key. So why is open architecture started to become attractive? So about 2.5 years ago, when I wrote my first article on LinkedIn about open architecture quantum computing, I received huge amount of hate mail, because everybody said that this technology is super complicated, quantum is different, we cannot do open architecture, it's too early. So I told people, well, I might be new to the quantum, but I have enough background in electronics that to be able to build open architecture systems is something that we've been doing for 30, 40 years, so we have to get started. The reason behind it again is that if you do buy a closed architecture system, it will become obsolete in the next 12 to 18 months. There is no two ways about it. These systems tend to be very easily upgradable, so you should be able to change and put in new QPUs by yourself, new electronics by yourself. It also acts as a platform for the innovation inside India. So for example, if you build a reference system and say in the beginning you bought your control electronics off the shelf from some company, the moment C-DAC has their own control electronics, we can easily remove the electronics from some other companies, stick in the C-DAC electronics and start to work with them. Or there could be other startups, there could be various other organizations. And again, it's a training ground for new talent, because open architecture quantum computers by their very nature are very robust. So we should not fear for students like yourself to be able to let loose in the lab, break it apart, put it back together. They don't break. And it lowers the cost, because as in the case of classical computing, we see the moment you open the architecture, it gives rise to competition and drives down cost. When we talk about open architecture from the cryogenic quantum computing perspective, so that's your superconducting and spin qubit types, we actually break it up into 3 broad bits. On top you have the quantum application layer, then the control layer, and in your cryogenic environment. If you deep down one more step into it, your quantum application layer can be broken up broadly into 3 parts. There's obviously the application layer where you think about the latest and greatest applications, might be looking for new chemicals, factory optimization, and so on and so forth. But below that, you need to have an ADE. So this kit is one of the things that we use. But again, I can't see any reason why people can come up with more innovative ways to do things better. And then you have, of course, your quantum circuit compiler. If you go down to the quantum control layer, so the first bit is the automation layer. That's where we operate as QuantrolOx, where we work on the automated qubit control and also make sure that it has the interfaces to execute the quantum circuits and also the error correction side. And below that, we have the actual control electronics, which takes care of the microwave pulses, which you need to fire at the qubits to get the right state of energy. And then inside the cryo environment, you have your signal paths with all your cables, attenuators, your QPU, and then finally your cryostat, which keeps the things nice, cold, and stable. So this is an example of a golden quantum reference system with interchangeable components using open architecture. Colonel Nath was at the lab in 2023 with Amit, where they saw the system. We opened it up for them and showed them that it doesn't break. A few months ago, there was also a team from C-DAC, Bangalore, that was visiting the facility. In this particular cryostat, we have about 5 different QPUs from different organizations. And on the rack on the left-hand side, we have the control electronics from the top 3 makers. And almost like on a daily basis, we swap around with the different control electronics and different QPUs, kind of just to show what a solid and well-built system this is. So why did we do that? So let's address the big challenge inside quantum computing and what's keeping us from getting useful quantum computers. Let's remind ourselves that how did this whole thing start? So we know that qubit development is slow, and hence since we started in 1999, we still haven't had any solid-state quantum computers. So Professor Nakamura came up with the first superconducting qubit. If I put it down to the world of classical computing, we got the first transistor in 1959 and the first microprocessor already in 1973. So that was around 14 years. But here things are much slower. End of 2024, we were still stuck at the sub 100 qubit era. So you can say 25 years of slow development. However, again, if you refer back to what McKinsey was saying, that by 2035, 1 to 2 trillion in value could be generated. It is debatable how much value will be actually generated, but what is not debatable that we need at least 1 million qubits to be able to get there. If we continue across with the way the things are going now, we're not going to get there. There's a big gap. How do we address the gap so that we can move from 25 years of slow development to taking giant leaps over the next 10 years to be able to get there? And again, that's what I like to remind ourselves. We are early. There's everything to play for. And hence, we should also think about how we can achieve leadership in quantum computing by building IP in India. So, when we talk about acceleration, what is it that needs to accelerate to get to 1 million qubits? So, the top 5 areas which scientists and engineers have identified in terms of getting to like 1 million qubits is we need to have better materials engineering. So, we can start to make qubits with much lower error rates than they are now. Advanced metrology, so that's the whole idea about when you make your QPUs or your materials, how fast you can do the characterization and testing cycles to be able to give you the data that you can do the next iterative development. And then there's packaging, optical communication, and various design and simulation tools. From our perspective, at QuantrolOx, we like to focus on the first two, which is the materials engineering and advanced metrology, and try to speed that up. One thing is clear that building or improving the qubits is not about science. So the science is very well understood. It is an engineering problem. And so based on that, let's look at your typical cycle of trying to engineer your qubits. So you will start with a theory where you think about your energy scales and noise sources, decoherence, processes, and so on and so forth. And then using that, you do your fabrication in the lab, where you spend quite a bit of time thinking about different kind of fabrication parameters, what sort of materials you're going to use, what are the interfaces, whether it's aluminium, whether it's cobalt, anything else. What is the kind of patterning and the cleaning technology you will use, because each of these will add defects to your QPU development process. And then lastly, we come to characterization, which is an incredibly slow and tedious process and is a big bottleneck in the course of development. To illustrate how big a bottleneck, let's look at some numbers. If you are trying to characterize even a single superconducting qubit, it takes days. So that's the industry benchmark, up to 48 hours to characterize a single qubit. Most of the labs take far longer. We know labs that take weeks and weeks. And the reason for that is that you have to stick them inside some sort of a quantum computer to be able to do the characterization process, and it typically takes 3 to 4 PhDs to keep even a 10 qubit quantum computer under control. The result that we see is, if we talk about again single qubit workflow, as I mentioned, 1 to 2 days, these are all the 15 odd or 16 odd experiments that you need to do to be really able to understand the characteristics of your qubit. And you cannot control your qubit unless you don't understand the characteristics of the qubits very deeply. And the problem we have is that no two qubits are the same. Every qubit is different, so you individually do the characterization. And there are no shortcuts. Similarly, even though you have fabricated your 100 qubit chip, that's only a function of you understanding that every qubit is good, but it's no guarantee that your two qubits will actually entangle to do anything useful, because that entanglement needs to happen for a gate to happen, and therefore you need to be able to test every single qubit entangled with everything else. So qubit 9 with 99, and qubit 4 with 32, 64 with 5, and so on and so forth. And all these combinations need to happen. Now, a single qubit workflow, when you get your wafer out, takes up to a week with the best PhDs working on it. So these are actual numbers from ETH Zurich, where it takes 3 to 4 PhDs up to a week to entangle even 2 qubits. So again, imagine 1 million qubits. We don't have years and years to wait to be able to get that. So that's where things like automation are important. Why is it slow? Because the tools that you have are very, they require a lot of manual intervention by experts. Your typical user interface for when you buy a control electronics essentially kind of looks like that. It's a Jupyter notebook with a command line interface. Imagine all of you are here using either Mac or Windows. Imagine if I removed your user interface and asked you to use your kind of web browser, your PowerPoint, your Excel, your email using your kind of web interface, where you had to write instructions to do all that. It would be very tedious. Similarly, out here with existing tools, if you are trying to do even simple experiments like your qubit spectroscopy experiment, you need to write code to do the experiment, you write some more code to do the analysis, you write some more code to essentially do your visualization. So it takes up to 4 or 5 hours to be able to do those experiments per qubit, and that's just one experiment in the sequence of 16 experiments that need to be. So it's not unusual to see people jumping between 30 to 40 different windows to do their experiment. So that's also a key factor where the whole process is slow. If you want to read more about it, sorry, the reference of that kind of paper mentioned, but the name of that kind of paper is How to Build a Quantum Supercomputer. If you need a reference, please come back to me, I'll point you to it. It's a 40-page reference paper. I really recommend everybody to read it. The 2 main points that basically come out from that is one, that as the number of qubits increases, the discrepancy between their characteristics also increases. So as you're trying to build bigger and bigger qubits, you can't get away from characterizing the individual qubits. And second thing, important fact is, as the TLS defects fluctuate, so that's the kind of 2-level systems. With the existing methods, as you get to about 1,000 qubits, everything that you have as of today makes your quantum computers unusable. So that's also the reason to work around it. Good news is these are all software things. India has the world's best software engineers, so we can be the leaders here. But saying, so let's move on to how we solve the problem as a Quantum Edge. So Quantum Edge is the product that QuantrolOx makes. It's a piece of software. It sits on a computer or a server, and it talks to the control electronics. And using that at microsecond intervals, it actually pings the QPU, looks at the state of the qubits, and then at microsecond intervals, it also makes decisions using machine learning, which essentially instructs the control electronics on what should be the frequency, amplitude, and the shape of the microwave pulses to fire at the qubits to get it to the right energy state. So you can have your quantum equivalent of ones and zeros. So it comes in 2 flavors. One is the characterizer, which is already being used by our customers in different labs in different parts of the world, which really automates the development and the production by automating the bring up, characterization, and tuning of qubits. And the second part is the entangler, which increases the uptime of the quantum computer from a typical 20% to 99%. Why is it 20% right now? Because on like a typical day, people spend about, I would say, 12-13 hours doing the calibration of the quantum computer, and about 2-3 hours using it, because by the nature of quantum computers, the moment you do a computation and you start to do the readout of your results, decoherence happens, so you need to recalibrate the quantum computer again. What makes us special, why I keep reminding people about the same photograph again and again, is that these things are real. So we have been able to build an open architecture quantum computer which we use for our own software development. We've been using it for 2.5 years. And that is also the reason why whenever we go to a lab and deploy our software, within anywhere between 2 to 4 hours, we are up and running. and that gives us very high level of compatibility with almost any quantum computer in the world. And we've tried many different architectures on superconducting qubits. We are already compatible with the top tier electronic makers, so gives us the highest compatibility coverage of any component in the quantum computing stack, and that was key. And by the end of the year, as our SDK comes out, we should also have compatibility to Keysight and also any open source or custom electronics which are based on the RF software. So that's also one of the steps which we are working here to with people in C-DAC on. Taking a step further, what's happening here? So it's a washout. So let's see what it's good. I have some. Because I cannot show a live demo, I wanted to show the a product introduction video. It's going to be about 4 or 5 minutes long, but it will give you a very good idea of what the product looks like. Hopefully the volume works, and what happened here?
Hi, I'm Timo. Did you know you can save hours or even days on qubit bring-up and characterization? These processes are critical steps to lay the foundation for more advanced experiments. With Quantum Edge, not only are these workflows up to 100 times faster than the current industry standard, but they also free you up to focus on what matters the most, your quantum research. Let me show you how. Quantum Edge automates superconducting, quantum computer tuning, and drastically reduces experiment times to seconds. This efficiency enables you to tackle more complex tasks like randomized benchmarking, advanced system optimization, and much more, all faster and with less effort. Getting started is simple. Once your chip is cool and your electronics are connected, Quantum Edge takes care of the heavy lifting, saving you significant time during the qubit bring-up and characterization. Quantum Edge is cloud-based, so it works directly in your browser. Just log in and you're ready to go. No complicated installations or extra setup needed. One of the reasons Quantum Edge fits seamlessly into your lab is its flexibility and built-in compatibility. You can easily define your architecture right here, tailoring it to your specific setup. Plus, as you can see, we provide a large library of predefined automation solutions for tasks like tuning and characterization. These workflows are designed to be intuitive, efficient, and ready to use out of the box. What's more, Quantum Edge integrates smoothly with major control hardware vendors, ensuring its compatibility with the equipment you already rely on. This out-of-the-box compatibility means you can get started faster with minimal adjustments and focus on running experiments rather than troubleshooting connections or configurations. From streamlining complex workflows to fitting effortlessly into your existing lab setup, Quantum Edge is built to save you time and maximize your productivity. One of the standout features is how easy it is to set up your own system configurations. Let's look at this further. Let's go ahead and click the gear icon in the left sidebar so we can access custom configuration options. Here we can add and describe new devices, create and adjust hardware configurations, and combine these into a complete system setup. Simple and effective. So, what about debugging then? We've all been there, nobody likes it. With Quantum Edge, this is also easy and straightforward. Let me show you. Here, we have a situation where a workflow has failed. We can see exactly where the error occurred. How to fix it? We can rerun the experiment with updated settings or parameters. And what is great is that you don't need any specific coding expertise for this. The user interface is designed to ensure possible issues are easy for everyone to understand and address. So, as you can see, Quantum Edge is a great help to maximize your time. You know, today, qubit bring-up and characterization and testing can take days, with a single qubit process taking 1 to 2 days. So, automation with Quantum Edge is the only way of scaling quantum systems to thousands or even millions of qubits.
Okay, thanks for your patience. So that gave you a nice view, but again, if anybody's interested, I'm happy to ask the team to host an online session. So I will not go too many slides on the product because I think that's quite obvious from the video. So let me just jump through a few of those. But let's come to the big performance benefits we've had. So as I mentioned, it takes 1 to 2 days to do these experiments with the biggest experts around the world. So we've been able to shrink that time down to actually under 10 minutes. So the fastest we achieved is 2 minutes. There's also some dependency on the quality of the qubits, but we always like to basically under-report our performance because it never goes over 10. Then as I mentioned, that really the kind of holy grail of quantum computing is not just to be able to check your individual qubit works, but how do you entangle the 2 qubits and that works. And then previously that used to take 2 qubit workflow up to a week by a few PhDs. We've been able to shrink that time down to below 25 minutes and fully automated. And the beauty here is that all these workflows, even I can run it, so you don't need to be a quantum scientist basically anymore, because ultimately what you're really interested is QPUs and not really banging your head with electronics and code. Just one case study from our partners in Taiwan, who actually lead the quantum mission there for Taiwan. So what they do is, like almost every organization, they work on 2 basically parts of qubit development. So one part of the organization is focusing on increasing the number of qubits, but because we still haven't found an ideal qubit that is scalable, so you always have another part of the organization, basically everywhere, including companies like IBM, that is focusing on small 2 qubit chips with the focus of doing very rapid experiments to try new materials and new structures. And before they started to work with us, that whole experiment used to take 1 day, and now it takes basically 12 minutes. At the APS March meeting, they'll be showing a new paper where the time has been significantly brought down. But I don't want to steal their thunder, so I will not say how much it is right now. One thing with quantum edge is we believe that we can add a 10x speed up every year. So we started by the end of 2024, we're 100x faster. By the end of this year, we are going to be 1,000x faster than the baseline, and then 10,000 in 2026, 100,000, and by 2028, we should be 1,000,000 times faster than the baseline. So the difference in the baseline is just not coming from our software becoming more efficient, but also the baseline becoming more complicated. Anybody here who has done any bit of qubit characterization, any hands here who's played with qubit characterization? So, okay, some people I know in the audience have. So one thing people need to understand is because of the quantum behavior and the sensitivity around qubits, if you tune your first qubit, great, you feel very happy. The moment you try to tune your second qubit, the first qubit goes out of tune, and then you have to do it again. And if you do your third qubit, then the first 2 go out of tune, and if you do your fourth qubit, the first 2. And especially when you do qubit pairs, the sensitivity also increases. So it's like a process by which you need to tune multiple things all the time. So your time to take qubit chips, larger qubit chips, doesn't increase in like a linear way, but more like exponentially. And hence the thing about the qubit kind of time and the speed up. So we really see ourselves as a key component for the quantum industry to be able to give them a viable path to be able to speed up the processes to get better and lower cost quantum computers. And the last part, I would like to really talk about what are we doing with C-DAC in India. So myself and Amit have been talking about this for a while, and we actually put together the proposal towards the ending of last year to essentially build this Pratham, which is going to be the Made in India quantum computing platform to accelerate the quantum education and research. And we hope that by Diwali of 2025, we'll at least be able to hand the prototype to the people in India to start building on. So what exactly is it? So we thought that let's start with a low-hanging fruit. What are the components do we already have? What can we basically package it to be able to seed it? Because seeding is always the hardest part. So we started off with the Rudra server that C-DAC already has. We put Quantum Edge inside it, and also Quniverse from C-DAC Bangalore, and created Rudraksh with a Q, which is the foundation around which we are going to build everything. That was the automation layer. Then the development effort with C-DAC electronics is already ongoing, where by hopefully in a few months we will be integrating the electronics at C-DAC with our software economy. And then C-DAC already has fantastic cloud access platform, so we'll be harnessing that. And then we will start to add the different QPUs being made in India, because there are a bunch of organizations, so I didn't want to basically list them, which ones are going to be there, but hopefully the ones from DRDO, ISC, or even we can always get a QPU off the shelf, so we can see how the different things work together. In the beginning, because we don't have our own dilution fridge, so the idea would be to have something off the shelf, but then within the next 3 to 5 years have like an Indian dilution fridge. And QuantrolOx really acts as the layer that makes the whole thing sing. So think of us as the conductor of an orchestra, for the lack of a better word. And this whole thing will be made in India. So again, we are super motivated to be able to execute that. And why are we doing this? So what will be the impact? We see that it will really create the kind of environment to have the Rudraksh, and the goal of like Rudraksh is eventually is not just to be sold in India, but we want to start to go and sell it internationally. Because that's going to be a key aspect of this entire thing, that every component that we build here, whether it is built in DRDO, DIAT, C-DAC, or any other Indian government organization, the focus should always be on commercialization. We have seen countries like Israel that are very good examples. They work very closely, productize, gain the revenues, and use those revenues to basically pump back and fund the R&D, right? There's a reason why Chanakya's book is called Arthashastra, because it's a book about economics. And without having strong economics, you cannot have a strong defense industry. So hence, my encouragement always is that whenever I see any piece of technology, the first thing that comes into my mind, both as an engineer and as an entrepreneur, how do we package it and start to sell it, right? So I see lots of people who are in the research community who actually come to me, Vishal, I don't want to do it. And I say, why? And they say, because I'm not interested in all the material things in the world. So I say, okay, you can do two things. Either you can give all that to me, or you can give it as a donation to your favorite engineering institute, because we need basically capital to be able to be a strong economy in a strong country. Anyway, so this we believe that we will have Bharat already on the map of a supplier of quantum technologies globally in 2025, starting with Rudraksh, then with the electronics and the QPUs and the dilution fridges, cables, flanges, what have you, and also creates a culture of international marketing, sales, and distribution. Also creates a habit of creating and marketable products. Harnesses India's demographic dividend, because the more you test your product, the better it is. And I was looking at Wikipedia and I found out there were 5,858 engineering institutes, right? So we have the largest market for educational quantum computers on the planet. If we build it here, it has to be a product that will sell internationally, because it will be the most tested one, and 1.5 million engineering graduates. Not all of them will come into the field of quantum computing, but almost all of them will have some benefit in being involved, and I'll explain why. So again, becoming a launchpad for research and development, and of course, if ordered in sufficient volumes by the government, then Pratham has the ability to see the economic model of these quantum computers. And we're not talking about hundreds. If the government commits to even basically 20 systems, so that even each of the IIT has it, the economic model is already there. And that is exactly how the quantum computing companies in the places like Delft and in Israel started, because the government committed to buying 5, 10, 20 systems. That's how Q-blocks, hardware, quantum machines, Zurich instruments, all have started. In terms of the technological potential, I think already we kind of mentioned that it will train and enable users, give us deeper understanding of when you talk about quantum computing, not just on the quantum algorithms, but the impact on quantum algorithms on the circuits, on the control, on the qubit, on the environment, and so on and so forth. And I mentioned to you that I'll give you examples on how Pratham could be a practical hand-on tools for all engineering students inside an engineering university. So if you're a civil engineering student, if you have Pratham in your lab, gives you an opportunity to really understand from the quantum computing site requirements, what are the needs for the chiller, vibration, thermal, noise, damping, plumbing, etc., which are non-trivial. We have cases that deviation of 5 degrees Celsius in the temperature when we were in Delft shut the whole lab down for various reasons I can explain. Mechanical engineering students will learn about dilation fridges, cryo pumps, precision mechanical components that give rise to other industries, connectors, holders, flanges, and the cryo thermodynamics. All these are areas of massive innovation and massive potential. They are so early. Anything that you find in the world today off the shelf from the top companies is simply not good enough. Materials engineering, so again, qubit quality, impact on properties, and also understanding the properties of the material when we thermal cycle them from room temperature down to the millikelvin temperatures. And of course, the kind of chemical engineers need to understand how to fabricate the cryo components, because the impact on everything that you fabricate at cryo temperatures is very different. Electronic engineering, low noise RF engineering. So we are still struggling with noise because the amplitude of the signals is so small in quantum. That's an area for improvement. Also, how the kind of nano electronics and cryoelectronics works. I understand there is already a project floating around in MIT waiting for approval for the kind of cryoelectronics. I think those kind of things really need to be sort of brought forward. Instrumentation engineering, how do you really make these new thermocouples that can work at these low temperatures, and of course computer engineering. So this is what I think is going to be an impact, and it will make a lot more people interested in the whole technology. And I wanted to come to an end of my presentation by saying that let's all work together to be able to build the best foundation for accelerating quantum development, and focus on improving everything from quantum materials to engineering to computer science. So thank you very much. So let's work together.
I need a measurement tool. So I use Apple binary code input output. That is the first part in lab, learning cryogenics, thermodynamic, pressure, temperature, measuring. At this moment I don't have it, all manually. Then I have to analyze it or report, make a report. Then I go to Microsoft to put it or documentation. Then if I have to go to big data, I need CERN workstation. So I'm using Apple as the instruments, Microsoft as a mediator, and then CERN workstation, which quantify my algorithm, which take 1 day, 2 days, 3 days, and which is the most expensive. So all 3 platforms, see, measuring something, reporting, putting laws, steady state, and things like that, to do the analysis and representation, getting the printing. So whole thing can be, because see, we are working on hardware, software on the quantum. Can we integrate all these, just a requirement, nothing else?
So absolutely did not get it. So the idea, so the question was that there are all these different tools being used to do the experiment, collecting the data, making reports, and so on and so forth. So the question was, can we integrate? And the good news is yes, that is exactly what Quantum Edge does. And so again, we can go through a much more detailed, basically online session with the team. So basically everything to helping with the configuration of the system, saving the configuration system. And one feature I didn't actually talk about is coming towards the end of second quarter is this basically lab book. So it's going to be cloud-based basically lab book. which saves all your data, but also the configuration of the system. Because right now repeatability of these experiments is very hard, because whenever you read a paper, you only get the data, but not the actual status of the instruments. So all that will be available via the kind of logbook. Every experiment will have a UID, and every person logging will have a UID. So people will be able to exchange their experiments through various education institutes inside India. And also when you publish an archive paper, you can give a UID of experiment, and somebody can just go and basically click it, go onto the cloud and run the experiment of the simulator. Has it answered your question?
Yes, sir.
Yes.
It's the beginning.
To superconducting quantum computers, or in terms of the competitors to our software quantum edge?
Software quantum edge.
Yeah. So we were the first ones to make the whole process automated. So some of the tools that are existing out there are the ones that come built in onto the control electronics. So for example, if you buy quantum machines, they have some built-in software to do basically qubit control, but it takes that much longer, as I showed in terms of the reference times. Some of the other tools that are specifically focused on qubit control in terms of software are the likes of this Cruise with a Q, that's based in Germany. So the window I showed about the command line interface is actually from them, so it's a command line interface. I would say at this point our biggest competitors are the basically in-house teams who we are trying to slowly and surely convince to stop using their own tools and use ours, which is normal, because why they use, because there was no tool available, and now people really want to build better QPUs. So for example, IBM said that their core IPU is in the QPU, everything else they want to buy from outside.
Does it work on surface corrected codes, quantum error, how does they calculate?
Yeah. Yes, it works with the error correction, but we don't do the error correction. We are the layer basically below the error correction.
The characterization means once the error corrected is done, so a logical qubit comes out.
Yeah.
Does the logical qubit is at par with different logical qubits? The way one physical qubit is, how close it is to other qubit, whether it is at the same time and space which we require. Does logical qubits also need to be characterized? And
So-
whether quantum edge does?
Yeah, so far we are not working up to that level. So what we are doing is we are going up to the this randomized benchmarking up to that level, and from there our goal is to get the qubits to a high level tune level, so that the kind of error correction can be applied and all that kind of logical qubit work can be done kind of more efficiently. So our goal is to reduce the whole basically overhead between the kind of physical qubits and the kind of logical qubits. So that's the layer we work on. If you want a deeper level answer, you'll have to talk to our director of product. So please send me an email and we can organize a session.
System which is operating on 5760 qubits, but the best of the IBMs, which is IBM Quantum, operating on 1121 qubits. So again sir, are the qubits only measure for the performance of these quantum computers?
Yeah, so computers, the quality of the qubits matters, and then this entire software layers in the stack and so on and so forth. So that's number one. And just talking about D-Wave, which is more of a analog quantum computer versus what IBM does, which is your digital or this kind of circuit-based quantum computer. A good way to think about it is the difference between an analog and a digital computer. Especially people in the defense have been using analog computers for a long time. So if you ever go to an old basically guns where the entire basically firing mechanism used to be an analog computer where you could basically feed in the at least I remember going onto a ship once where you could basically feed in the kind of parameters with respect to the speed of the ship and the wind, etc. And it would do the kind of calculations. So analog computers are very efficient, but for a specific problem. But once digital computers become more kind of powerful, they start to replace them. So I think we are at a stage where there are certain things that you can do with D-Wave that you can't still do with IBM. But then on the kind of flip side of an analog computer is that it takes a very, very long time to program a D-wave computer to do anything, right? So there are all these pros and cons. But, yeah. Okay, so on that, so there is no standard measure as of now on the way quantum computers are done, because everybody is using their own basically ideas, because every single quantum computer out there is good at one thing, and as with any engineering compromises, if it's good at one thing, it's not very good at something else. So I can pretty much tell you that everybody who reports their basically numbers that we are fantastic at this, they are basically cherry picking the data. So unfortunately, we have not come up with a normalized way of looking at the benefit of a quantum computer, and the day we will start to be able to come out is the day we start to do something basically useful. So even when you take something like Shaw's algorithm, everybody compares stuff, right? And it's very hard to figure out what is better. Until 18 months ago, everybody was talking about a quantum volume, and IBM introduced the idea of quantum volume because they came up with a metric on which they were very good. But the moment Continuum came up with a way to beat their quantum volume, IBM stopped talking about quantum volume, right? So everybody is kind of literally coming up with invented basically benchmarks. Which is the right benchmark, we just don't know.
So, sir, thank you for the wonderful presentation. And you have brought out the engineering problems really well in that summary sheet. So my question was, are the science problems also summarized in this way, or are they over, or only engineering problems remain?
So I think a very good question, that are the science problems all summarized and solved, are only the engineering problems remaining? If I say there are very few science problems, I think the scientists will not be happy with me, but I think, as an engineer, so we know enough about the behavior of the kind of quantum physics and materials, etc. And now it's a point of a definition. So if you are doing materials, are you doing materials science or doing materials engineering, right? So at least in my head, because I, as an engineer, went to study materials. So when I was put at a research center at the National University of Singapore years ago, so I was doing a lot of material and device fabrication. And to me, it wasn't science, it was really a lot of engineering. But I think that's a debatable definition. But a good kind of paper to read on that is how to build a quantum supercomputer, and that so far is one of the best outlines of even, I would say, some of the scientific challenges. But yeah, I will send you the paper, and then you can basically tell me what you think from your perspective.
Okay.
Thanks.
First semester, I just asked the first semester. So mainly in communication, quantum communication.
What was your bachelor's?
In computer science.
So, on computer science side, then there is the whole issue around working on transpilers, which is again a kind of problem on the which is a computer science problem. Then there is a question related to, okay, when I talk about transpilers, what do I mean? So how do you take the thing from the quantum algorithm to circuits, and from the circuits, how do you think about generating them into the electromagnetic pulses? And I think that's an area which has not yet been done well. So it's a very, very sort of a manual way. And we also as a company are very much interested at that kind of a transpiler layer. Then there is quantum information science, which almost, since you're from the computer science background, I would say start with that and then work your way down the stack. Yeah.
Thank you all the participants for asking your
I
questions.
have, excuse me, sir. I have one question and a question. Reference to your slide number 56, you have highlighted many domains where interventions from skill set can be implemented. One which is missing from there is design, which implements usability, interaction, aspect of implementation of quantum computing. For past couple of years, I have been working in this area, trying to put up a startup which can actually intervene in developing such use cases where interaction can help reduce the resistance of adoption of quantum computing, help researchers and students to have quality outputs. As a word I forgot, I really forget some of the terminologies usually, but interpretations, to have meaningful interpretations. And that's where I think QuantrolOx can really extend a help and a hand to this venture. It's called QRhythm, and we are totally focused in this area where user interaction and usability can be part of it. And here to the audience, we are open to internships and young scientists to come and be part of that. And any help and your comments will be really helpful.
The first person we hired before we wrote a single line of code or hired any engineers was a user experience researcher, right? And I'll explain why. So I mentioned that people are jumping between 30 to 40 different windows to do their qubit control. So our speed, when we compare to humans versus us, part of the speed comes from the machine learning smarts that we have. Part of it comes from our software architecture. A big part comes from the usability improvement. So in the early part of my career, I was also working in manufacturing operations. So we used to really focus on how the production line worked and how people operated. So this user experience person spent weeks at different research labs around the world just observing how scientists did their experiments. And we actually interviewed them and we did that, and then we came up with ideas on how the UI flow should look like, and then we used to go back to them and actually design. The reason the software is so intuitive is not by accident, is through sheer hard work of over 12 months in refining the UI, and we are still refining it because there are a lot of concepts going forward, especially how do we represent like 1 million qubits, right? I mean I can represent 100, but how do I kind of logically give an idea of a 4 million qubits? And so I think what you're doing is exactly what we need, right? So we should definitely talk. Yeah.
And one aspect which I guess
It is yeah.
We really need to improve in that area.
100%,
Especially with the
agree.
government and the scientists over here. Not only we should look towards becoming use case capital, just like we are looking for AI for us to work on, or for in future for quantum to work in the engineering problem. We should also look towards becoming the superpower of catering usability and user experience problem of the world. That potential we have the best institute and best of the best researchers in this area. Only thing is we only need the interaction and the integration with the technical community. Thank you.
Peace and forward-thinking vision you've shared with us today with respect to qubit automation. I now request Colonel Retired A.K. Nath sir to kindly felicitate sir with a memento.